Okay, so the next thing that we have here is some part about resistors. I will basically read through the text wherever it's necessary. I will add a couple of things if I can. So it says that resistors are used to control the current that flows through a portion of a circuit. And what that means is that you use a resistor in order to, well, control the current that flows through a portion of a circuit. What that means is that, for example, if you have a simple circuit, for example, some power supply over here, and you have some resistor over here, and this goes back to your power supply. Now suppose that this is a portion of a circuit. Now in this portion of the circuit, basically you have some voltage over here and you have some resistance, and based on the voltage and the resistance, some current is flowing through your circuit, flowing through this branch of the circuit, because V is equal to I times R, meaning that basically then I is equal to V to R, meaning that basically meaning that the current that is flowing through your circuit is nothing but the ratio of the voltage and resistance. So voltage to resistance is current. So what that means is that basically, usually, of course, based on the constraints imposed on you designing the circuit, you have to set your voltage to basically some you have to when you want to basically design some circuit, you have to choose some sort of power supply for your whole circuit, meaning that you cannot, there are all of these different parts of your circuit. There is some part over here, there is some, for example, oscillator here, there is some, I don't know, some other part over here, some other part over here, and some other part over here. And usually what happens is that, for example, the input of every part of the circuit is doing something, of course. For example, thinking about the radio, the signal comes in from the antenna, and then it will get either attenuated or a little bit basically, or a little bit the signal will be either basically toned down or strengthened depending on that, on the situation. And then it goes through some filters, for example, and that filter gives it to some other, for example, part for decoding or encoding or something like that, and then that output goes to some other part of the circuit, some other part of the circuit, some other part of the circuit, and so on and so forth. And then, for example, suppose that in the last stage, so you have basically something like a speaker, and you will hear, for example, some sort of sound coming out of some speaker, and you will hear somebody else talking on some other radio, for example, 100 kilometers away from you, or 100 miles away from you. So that's basically how a radio works is inside a what you would call a radio, or inside that box there is a circuit board, and on this circuit board all of these modules are laid out basically on different parts of the circuit, and they work together in order to basically do what is supposed to be done in the case of that circuit. Now all of these parts, of course, need power supply, and depending on your particular situation over there, sometimes every part needs a different, for example, supply voltage from the power supply. And suppose that, for example, this is your power supply over here, and you usually have one single power supply for the circuit. It goes to different parts of the circuit. So now if now there are basically different ways to regulate voltage and give basically, for example, suppose that you have this V of S over here. You have this V of S over here. Let's say that your V of S over here is 12 volts DC. If you want to bring it down to, for example, 5 volts DC for this part, you can use some circuit called, for example, a voltage regulator to do that. Or suppose that you need, for example, 6 volts DC for this part. Again, you connect this circuit to this part and create 6 volts DC for this part of the circuit. But sometimes, yeah, this is all about the voltage. Sometimes you need to basically, sometimes you need to have control over the current going through a circuit. And in those cases, you can use a resistor, because as I mentioned, basically the current is basically a ratio of V and the voltage and the resistance. So supposing that, for example, the voltage is set and you set it to some set voltage, for example, then if you keep changing this resistor, then this current keeps changing and you can control it that way. That's basically what you can do with the circuit. Of course, all of the explanation that I went through, I thought it would somehow basically lead us into basically current, but that was a different story. Anyway, that's of course not wrong, but not very relevant here. You will be able to use it somewhere, of course. Now, basically, you can use the Ohm's law that we have discussed over here. You can use the Ohm's law to select the value of a resistor that gives you the correct current in a circuit. For a given voltage, the current flowing through a circuit increases using smaller resistor values and decreases when using larger resistor values. So you can see that since R in this relationship, R is in the denominator and I is in the numerator on the other side, the relationship between I and R is basically an inverse relationship, meaning that if you increase your R, your I is going to, if you increase your R, your I is going to decrease, and if you decrease your R, your I is going to increase, meaning that for higher values of a resistance you will get lower values of current. For lower values of resistance, assuming that the voltage is not changed, for lower values of resistance you will get higher values of current. So that way you can control the current going through a circuit. Now this resistor value works something like pipes that run water through a plumbing system. For example, to deliver the large water flow required by the water heater, you might use a 1-inch diameter pipe. To connect a bathroom sink to a water supply, to connect a bathroom sink to the water supply requires much smaller water flow and therefore works with 1/2-inch pipe. In the same way, smaller resistor values, meaning less resistance, increase current flow, whereas large resistor values, meaning more resistance, decrease the current flow, which is something that you can understand based on this relationship here. Now there is something in these resistors called the tolerance. And usually the tolerance of a resistor is either I don't know, 5% or is 2%. I don't really know if that exists really. There is 10%, and there are different basically values for the tolerance of a resistor. And what that means is that basically when you have a resistor, you usually, as I showed you before, the resistor is basically some very small cylindrical thing like this, which is, well, but it's a very, very small cylindrical cylinder, basically, you could say, with two leads coming out of either side of your resistor. And there are basically these color bands on your resistor. So for example, suppose that, and there are all of these color codes. For example, you can see that over here, for example, 0 is black, 1 is brown, 2 is red, 3 is orange, yellow becomes 4, green 5, blue 6, violet 7, gray is 8, and white is 9. Okay, so for example, you have a resistor over here. On the first band you have white, and then you have blue, and then you have gray. So these three colors over here, that tells you that your resistance is basically is 9, and then you have a blue is 6, so that's 9, that's a digit 9, a digit 6, and then this third digit over here, this third band over here, is called the multiplier. So these two first ones are the first digit and the second digit. The third digit, of course, this is all provided that you have 4 bands on the resistor, because there are some resistors that have basically 5 strips over here. There are some resistors that have basically 6 strips over here, or 5 strips, and so on and so forth. Now, provided that you have 4 strips over here, the first 2 are the first digit and the second digit. The third digit the third band over here is the multiplier. For example, and you have all of these colors, and there is a couple more that you wouldn't get, that you would not have in the first 2 digits, meaning that, for example, you see over here the silver. We don't have silver over here. Silver is not here, but silver and gold are over here. So you have silver and gold over here, in addition to what you have over here. And what that means is that, for example, if this third color band is, for example, a black, then what that means is that you take the first 2 digits and multiply it by a 1. If it's a brown, then you multiply it by a 10. If it's a red, you multiply it by 100. Then you multiply it by 1k, 10k, 100k, 1 meg, and 10 meg, 100 meg, and so on and so forth. And when it comes to until all the way up to 1 gig, which is 10 raised to the power 9. And then there is also some multipliers that divide basically. So if you get gold over here, you're supposed to divide by 10. If you get, for example, silver over here, you have to divide by 10. So these are your multipliers. And then there is something called the tolerance, and you get essentially all the colors except for example, you don't have, for example, black over here. Silver, gold, gray, violet, blue, green, yellow, orange, red, and brown, but there is no black over here, as you can see. So this is the tolerance of your resistance. for example, if you have the color gold over here, that means that the value of your resistance is plus or minus 5%, or actually that the value of the tolerance is 5%. Basically, you would call that a 5% resistor. If you have silver, for example, that's 10%. If you have gray, it would be 0.05%. If you have violet, it's 0.1%. If it's blue, it's 0.25%. Green is 0.5%. Yellow is 4%. Orange is 3%. Red is 2%. And brown is 1%. I used to not pay much attention to these things. You usually don't really pay much attention. Although, if you're into designing circuits and that sort of thing, of course you have to pay attention to all of these things, because you don't want to choose the right type of resistor for your circuit. But for example, what I used to do was repairing electronic devices and that sort of thing. So in that sort of work, you don't really pay much attention to, for example, the tolerance of your resistors. And that's basically that. So that is basically how you read a resistor when you have 4 color bands on your resistor. Now there is also some kind of resistor where you have 5 strips over here. So you see 1, 2, 3, 4, and 5, and you have the first digit, the second digit, and the third digit, and then you have the multiplier, and then you have the tolerance. And so here you will have more control over the value of resistance that you can choose. For example, in this combination, you can go with 9 and 6, and for example, it's, I don't know, 0 or a blue over here for the 1, and then you would get 960 ohms, for example, for this resistor with some tolerance. For example, the tolerance is not important, but there is no way to get, for example, 965 ohms as the value of the resistance here, because that digit is simply not there. But over here you can actually do that, meaning that you can go for 9, and you can go for 6, and you can go for 5, and that, for example, the multiplier, you get the blue, and it gives you 9.65K or 965, and then here I need a black actually, because I need to multiply by 1. So this gives me 965 ohms exactly. But over here, it's actually not possible to do that. It's simply not possible. So that's basically that. And I will continue this. I need to tell you a couple of things about these resistors, and then you will be on your way to ordering your resistors on, I don't know, there are thousands of websites these days, but there are some other ways to get your resistors as well. We will talk about them as well. Okay, so basically we talked about a couple of things here. We talked about these resistors, basically 4 strips, 5 strips, and so on and so forth. So the difference between the 4 strips and the 5 strips is basically, it's very simple. So you get the first digit over here, the second digit, and the third digit, and then you will get the multiplier, which is just for example, these 3 digits, for example, multiplied either by 1 or by 10 or by 100 or so on and so forth. And then the last digit is again going to be the tolerance. And over here you have basically the first digit, the second digit, the third digit. You have 3 digits over here. When you have 6 strips, you get basically these 3 digits over here. Then you have again, you have the multiplier, and then you have the tolerance, and then there is something over here called the called the temp code, whatever that is. I don't really know. Let's see what this is. Okay, temperature coefficient. So there is some temperature coefficient, and then if you have that coefficient, you can, meaning that based on the temperature, you can, of course, based on the temperature, the resistance of your resistor is going to change. Okay, let me close my door. Okay, so you see what happens is that basically when you put the resistor in a circuit, suppose that you have this resistor over here in this circuit, okay, and you have some voltage basically parallel to the resistor. You have connected your power supply to the 2 leads of the resistor. So now what's happening here is that basically current is going through this circuit, this resistor basically, and of course working is being done, meaning that current is going through the resistor is resisting the flow of current. And so what happens here, the resulting the whole process basically results in heat building up in your resistor. The resistor gets hotter and hotter, and then the heat that is produced on your resistor depends on some factors. For example, depends on the amount of current going through that, and then also depends on some other characteristics of resistors, which is basically the wattage of your resistor. So for example, there is something called, I suppose, wattage is called, or whatever that is called, I don't know, but what the concept is that, for example, there are resistors that are very small. They are 1/8 watts. They are called 1/8 watt resistors. There are resistors that are 1/4 watt resistors. There are resistors that are called 1/2 watt resistors. And then you can go all the way up to, for example, 1 watt, 2 watt, even, I don't know, probably 5 watt resistors, and so on and so forth. As you increase the wattage of the resistor gets bigger and bigger and bigger for the same amount of resistance. For example, a resistor, for example, a 20 ohm resistor that is 1/8 watts would be something like this. The exact, the real basically size of the resistor, if you saw it on the palm of your hand, it would be something not bigger than this. Now the same 20 ohm resistor, if it's a 10 watt resistor, then it's going to be something big, something like this. That would be a cuboid. It would be a cuboid, something this big, and it has basically these leads over here. Okay, and it would be very heavy, and with a metal heat sink, and so on and so forth. So as you increase the wattage, of course the body of the resistor is going to grow and grow. And now what happens is that, for example, suppose that your you have a 5-volt power supply, and you have some resistor over here. Based on the voltage of your power supply and the current that is going through your resistor, there is some work being done over here, which is measured in watt, for example. And watt is basically, we will get to that as well, but watt in short is the product of voltage and current. So the voltage which is present on the 2 leads of the resistor times the current that is going through the resistor is basically the work being done in the resistor, which is usually, of course, heat. Now, for example, suppose that you have this this exact scenario over here. Okay, you have this exact scenario over here. You have this resistor over here. Let's say that it's a 20 ohm, for example, resistor. R is equal to 20 ohm, and your voltage is 5 volts, for example. So now the current that is going through your resistor is basically I is equal to V to R, which is equal to 5 divided by 20, which is equal to 1/4 amp, which is equal to 0.25 amps. 0.25 amps, which is 250 milliamps. Okay. Now the voltage that is present on the 2 leads of your resistor is the voltage of the power supply, of course, meaning that if you measure the voltage over here, it's equal to 5 volts, and the voltage that you would measure over here would also be 5 volts. So then if you want to calculate the amount of the wattage of the what do you call it? They call it I don't remember the words. Anyway, that doesn't matter. We will get to that. But if you want to calculate the amount of work being done on this resistor, which is called P, standing for whatever that is, we will get to that, which is indicative of the amount of work being done in the resistor in the form of heat, that is equal to VI. So now P over here would be basically V, which is 5 volts, times the current going through the resistor, which is 0.25 amps. Now 5 times 0.25, 5 times 0.25 is equal to 1.25 watts. Is equal to 1.25 watts. Okay, so what that means is that, now I don't exactly know, I mean, in terms of physics, I don't exactly know what this exactly represents, but I know that it is very, very closely related to the amount of heat dissipated by this resistor, meaning the amount of work being done actually by this resistor as a result of the current going through the resistor, basically. So the power over here, this stands for power. This stands for power. So the power dissipated over here is 1.25 watts. Now if you put a resistor over here, if you use for example 1/8 watts resistor, which is a very, very tiny small resistor, it would burn in just a few, probably in 10 seconds or so, because it would get hot and it would just simply fry and burn. So since the power dissipated on this resistor is, for example, 1.25 watts, you want to put at least, the resistor that you basically want to use here is at least a 2 watt resistor, not less than that, or at least 1.5 watt resistor or something like that, with the same, of course, amount of resistance that you need over here. So that's basically all the concepts about basically the heat dissipated from a resistor and the wattage or the power of a resistor, and so on and so forth. Now the problem is with these resistors, the problem is that, and probably with any other chemical material, and of course you know that resistor is a chemical material. It's basically carbon. It's carbon basically packaged in a small package, and that creates resistance. Carbon probably, of course, with other things basically mixed with that. Now the problem with that is that when your resistor in the circuit, when the current is going through your resistor and your resistor is getting hotter and hotter, as it gets hotter, the value of the resistance of the resistor is going to decrease, not increase. I'm 100% sure that it's going to decrease, because I have actually measured that practically. The hotter that your resistor gets, the more basically the amount of the resistance is going to decrease, and that of course results in the current going higher and higher, because your resistance is decreasing and decreasing. So now in some circuits this is important. For example, in an oscilloscope, for example, an oscilloscope is something with which you can for example, you can basically measure voltages over time and so on and so forth, and you would get a graph on your oscilloscope. It shows you how the voltage is changing versus time. This is voltage and this is time. So the oscilloscope shows you how the voltage is changing over time, versus time, or over time, you can say. So in an oscilloscope, of course, the more that your oscilloscope is running, the hotter is going to get everything in your oscilloscope, including all the resistors in your oscilloscope, are going to get hotter and hotter. So in that case, for example, you would, if it's really important for your, for example, in an oscilloscope everything is calibrated, meaning that, for example, when your oscilloscope gets hotter, if things are not calibrated, then of course the output signal that you see on the CRT TV of the oscilloscope is going to change. Basically, is going to change as a result of everything in oscilloscope getting hotter and hotter, because as it runs more and more, everything gets hotter and hotter, and then for the same voltage you're going to get a different shape of a graph on your output, and then your reading would simply be wrong, right? So you don't want this to happen. So for this kind of purpose, you can, for example, one way that you can solve this problem is that you can for example use the kind of resistor that you want to use the kind of resistor whose behavior you can anticipate. And that is, now this kind of resistor, for example, this 5-strip resistor, it has no temperature coefficient. So you don't know really what's going to happen if the temperature of the resistor rises, for example, 5 degrees or 6 degrees or 7 degrees and so on and so forth. But this resistor, of course, these are a little bit more pricey, more expensive, but then over here you can anticipate what's going to happen. For example, if temperature rises by, for example, 10 degrees or 20 degrees and so on and so forth, and then based on the information that you have, then you can basically design your circuit in a different way, so that then ultimately the output of your oscilloscope is basically always the same graph for the same voltage, meaning that it's just simply not acceptable that, for example, when you turn on your oscilloscope and connect it to some voltage, it shows you, for example, this graph over here, this being, for example, V1, and then after a while, when it gets hotter, you connect your oscilloscope to the same voltage, and then it gives you, for example, this graph for the same voltage, and this is, for example, V2, and clearly V2 is much higher than V1. And then of course you're reading this and you're making all kinds of decisions based on what you read on your oscilloscope. So this kind of thing is not just simply not supposed to happen. So you have to basically take care of that problem. So that's basically where you can, for example, one way that you can use the temperature coefficient. Now, so basically to wrap this up, in the resistors, where basically you have 1, 2, 3, 4, 5, 6 strips over here, the first 3 strips are related to the first, second, and the third digit. The fourth strip is related to the multiplier. The fifth strip is again the same thing, tolerance, so there is no difference. I mean, in that respect, is basically the same thing that you see on a 5-strip resistor. But in addition to all that you have on a 5-strip resistor, in a 6-strip resistor you have this temperature coefficient in the end, which tells you about the temperature coefficient of the resistor, which is, for example, the coefficient here is 5, 10, 25, 15, 50, 100, and based on the data sheet, probably you can make sense of these numbers and you know what to do with them. So that's basically that. Now there is still some material over here. I will go through them as well to see if there is anything in there to talk about, and then we will get past these resistors. Okay, so now basically what remains here is we talked about almost everything, but not about the resistance. First, there is basically there are some colors that you need to know to understand. So these colors you will learn. I mean, usually what happens is that you have a small chart, for example, and that chart you keep I mean, by your side on your electronics bench or wherever it is that you work. And then whenever you want to read the value of resistors, you can consult your chart, and then after a while you will learn the colors. Of course, it's just like 10 color codes that you need to learn. So then there is basically these colors, like the black is, of course, this is all related to the significant figures. So you have, suppose that you have these. Basically, you have these bands over here, 1, 2, 3, and for example, the 4. And basically, you have 4. The fourth. Let's say that this is a 4 band, for example, resistor. So the first one, of course, is the first digit. This is the first digit. This band over here is the second digit, and then the third band is the multiplier. And the fourth band over here is the tolerance. Now these 2 digits have been called basically the first digit, and the second digit have been called the significant digits. And of course they are actually the significant digits, because other than that you will have some multiplier only. And the colors related to the significant digits that you need to know is basically black is 0, brown is 1, then 2 is red, so red is 2, 3 is orange, 3 is orange, and then 4 is yellow. Yellow is 4. 5 is green. Green is 5. And then blue is 6. 7 is violet. Violet is 7, and 8 is gray. 8 is gray. Gray is 8, and white is 9. And white is 9. So 0 to 9. And then for the multiplier, as far as the multiplier is concerned, so these are for the significant figures. Now for the multiplier, if you want to use the same colors for the multiplier, black is basically you need to basically multiply your significant figures by for example 1, or 10 raised to the power, which is 10 raised to the power 0. 10 raised to the power 0. Now over here you need to multiply by 10 raised to the power 1, I suppose, which is basically 10. Over here you need to multiply by 10 raised to the power 2, which is 100. Over here you need to multiply by 10 cubed, which is equal to 1000. Over here you need to you need to multiply by 10 raised to the power 4, which is a 10,000. Over here you need to multiply by 10 raised to the power 5, which is a 100,000. And here 10 raised to the power 6, which is 1 million. Which is 1 million. Over here you multiply by 10 raised to the power 7, which seemingly doesn't really exist. I've never seen basically such a color on the third band. And you have two more colors here, which are basically, if you have basically gold in the third band or in the multiplier band, gold is basically 0.1, which is 10 raised to the power negative 1, which is equal to times 0.1. And if you have silver, silver is 10 times 10 raised to the power 0.2, which is equal to 10 raised to the power, 10 raised to the power negative 2, which is equal to 0.01 basically. Now so gold is times 0.1, or 10 raised to the power negative 1, and silver is 10 raised to the power negative 2. Now as far as the tolerance is concerned, so these are basically all the way up to blue. So this is blue, and these are, what that means is that, for example, if you have black in the multiplier band, that means that you multiply by 10 raised to the power 0, meaning that you take the significant figures and multiply them by 10 raised to the power 0. If you have brown in the multiplier band, you multiply that by the significant figures, you multiply by 10 raised to the power 1 all the way up to here. And then if you have these two colors in the multiplier band, you take your significant figures and multiply by 10 raised to the power negative 1. Or if you have silver, you multiply by 10 raised to the power negative 2. Now, as far as the tolerance is concerned, of course there is all kinds of colors over here, but for at least in the beginning you don't really need to know all of those tolerance colors, because they're just simply not there, meaning that they're not that usual, and so you will not simply encounter any of them, most probably, unless you come across some unusual type of resistor, or if you for some very specific purpose happen to order one. Otherwise they're not simply there. So for the beginning, as far as the tolerance is concerned, you have basically the tolerance band, which happens to be basically the fourth band on the resistor, the fourth band on a 4-band resistor, you have basically brown. You have brown, you could have red, and you could have gold or silver. Gold or silver. Usually these two are more, usually these two are the ones that you usually meet on a that you happen to see on a resistor on the tolerance band, because the brown refers to plus or minus 1%. So this is a 1% resistor, or the tolerance is 1%, which is a very low resistance, very low tolerance, which is not what you usually would what you usually have basically in your resistors. Or for example, red basically refers to, for example, plus or minus 2%, which is usually not what you happen to have. But then you either have a 5% resistor, which is gold is 5%, is plus or minus 5%, and silver is plus or minus 10%. You usually work with this kind of resistor, 10% tolerance. And what this means is that suppose that you have a resistor that says that, for example, you have for example, 1000 ohm resistor, the color code would be 1 0, and then supposing that it's basically 1 2 3 and 4 bands over here, the last one is being the tolerance. The first two would be the significant figures, so that significant figures would be 1 and 0, and then you have to multiply by 100. Multiplying by 100, so you need 100 over here, which is a red, right? Which is a red. So 1000, and so this would be the first significant figure. This would be the second significant figure. This would be the multiplier. And this would be the tolerance is some color. For example, let's say that your tolerance is 10%. So you would have some color over here, which would be, for example, a silver. So let's do this resistor over here. Let me draw it over here. So suppose that you have a 1 which is a brown. So I draw a brown over here. Let's say that this is a brown, and it's not a very good brown. Let's say that this is a brown, and then you have a 0 which is a black. So you have a black over here, and then you have a multiplier 2 multiplied by 100, which is a red. So you would have a red over here, and then you would have, for a 10% resistor, you would have silver. Silver would be something like this. So now to read this resistor, what you would do is that, you have 4 bands over here. The first band is your first significant figure. The second band is your second significant figure. The third band is your multiplier. The fourth band is your tolerance. So the first significant figure is a brown, which means a 1. Which means that you have a 1 as the first significant figure. The second color is your second significant figure, which is a 0. It's a black, which means a 0. The third significant figure, which is a red, means that you have to multiply this by 100. So 10 times 100 is 1000. And that would be in ohms. Whatever you got over here would be in ohms. and then your tolerance, which is the silver, is plus or minus 10%. Plus or minus 10%, which means that now 10% of 1,000 is, of course, so if you have 1,000 times 10%, it would be 10, that would be 100. So that would be 100. And what that means is that now 10% of 1,000 would be 100, so that would be plus or minus 100 ohms, basically. That would be plus or minus 100 ohms. So that means that this is 1,000 ohms plus or minus 100 ohms, which means that if you subtract 100 from 1,000, you will get 900 ohms, and if you add 100 to 1,000 ohm, you will get 1,100 ohms. So that means that the value of your resistance is somewhere between 900 ohms and 1,000 ohms. That's basically what this tolerance means. Now let me get my calculator. Okay, so as you can see, what that means is that when you get 1,000 ohm resistor, 1,000 ohm 10% tolerance resistor, all that you know about this resistor is your actual value. The actual value of the resistance of this resistor is somewhere between 900 ohms and 1,100 ohms, which is basically a pretty big, basically, tolerance. Now, the less your tolerance, the higher, I mean, the less your tolerance, basically, the smaller would be this gap. And as you can see, for example, in the case of this 1,000 ohm resistor, then for example 1,100 minus 900 would be 200 ohms. So there is this room over here, 200 ohms, between which the actual value of this resistance can be pushed back and forth. So for example, if you go for a 5% resistor with the same specifications, with the same 3 colors in the beginning, of course this would be that would be 1,000 ohms plus or minus, for example, 5%, and 5% of 1,000 ohms would be just 50 ohms, which is basically 950 ohms, and the upper limit would be 1,050 ohms. That means that the actual value of the resistance of this resistor is going to be somewhere between 950 ohms and 1,050 ohms. And well, again, the same thing. I mean, you could go for a resistor which has for example, 2% tolerance. So 2% tolerance would be in the case of for example, 1,000 ohm resistor. Again, 1,000 ohm resistor plus or minus 2%. 2% would be just 1,000 times 2% is 20 ohms. So then you would get basically 980 ohms, and the upper limit would be 1,020 ohms. So then your R is somewhere between 980 and 1,020, and 1% would be just 10 ohms. So that would be 990 ohms, and for example, this is in case of 2%, and that would be, for example, 1,010 ohms. This would be in the case of 1%. So as you can see, the lower your tolerance, the higher is going to be the closer is going to be the actual value of the resistance to the stated value of the resistance on the resistor in the form of these color codes. But of course there is a problem. These resistors are relatively very costly, so you usually don't you usually don't need that much precision, or so you don't really most of the time you just don't buy them for ordinary purposes. For ordinary purposes you usually use a resistor which is, for example, a 10% resistor. If for a specific purpose you need a resistor which is very accurate, then for example for that purpose you would you would order, for example, a couple of those resistors, and that's usually it, because these are usually very expensive, compared to a 10% resistor, for example. And in case you're interested in some theory about these resistors, so here it says that most electronic circuits are designed to work with resistors with plus or minus 5% tolerance. The most commonly used type of resistor with plus or minus 5% tolerance is called a carbon film resistor. It's called a carbon film resistor. Create a new layer here. It's called a carbon film resistor, and this term refers to the manufacturing process in which a carbon film is deposited on an ice insulator. The thickness and width of the carbon film determines the resistance, meaning the thicker the carbon film, the lower the resistance. And carbon film resistors work well in all the projects of this book. So if you want to purchase resistors, carbon film resistors would be basically would be suitable for the projects that we do in this book. Although when we get to that stage, I'll show you some places on the internet where you can basically find your resistors and other electronic components. And on the other hand, precision resistors contain a metal film deposited on an ice insulator. The thickness and width of the metal film determines the resistance. These resistors are called metal film resistors and are used in circuits for precision devices such as test instruments. And test instrument is basically, for example, you can think of that example I gave you about that oscilloscope. That the test instrument has to be accurate. So in the case of test instruments, you use precision everything, not just resistors, but precision capacitors, precision resistors, precision even transistors that are used in there are transistors that have been, in most cases, for example, if you look at some oscilloscopes from, for example, from Philips, for example, or some oscilloscopes from I don't know, I happen to have, for example, an oscilloscope from Philips. They usually basically either manufacture their own parts, or they basically order them to be manufactured based on their own specifications, because they're supposed to work in their own circuits the way that they have basically the way that they have designed those circuits. So you cannot design a circuit and then use any sort of electronic component in there if the circuit happens to be some sort of circuit, for example, related to an oscilloscope, because there you need a high level of accuracy and dependency, basically. So that's basically that. Now I'm going to end this video here, and in the next video we will talk a little bit about how you can basically put resistors together, put them back to back, parallel, series, and out of them get different kinds of resistors. So I'll see you in the next video, and thank you.